Hi guys, Shouvik here. Welcome back to your channel. So today we'll solve another question from Leetcode itself. So let's get started. Yes. So today we have the question: lowest common ancestor of deepest leaves. Yes. So on these questions, they are given a root of a binary tree, and we have to return the lowest common ancestor of its deepest leaves. There are a couple of things you guys have to know, what is the lowest common ancestor, and there is and I have to say the basic tree traversals. These tools are prerequisites, but if you are by chance you don't know, I will just quickly give you a brief. But for lowest common ancestor, I have used my own templates of tree lowest common ancestor code, and it worked as it is, just a minor tweak. So if you need more details in depth of that particular portion, so please do comments on that. I will create a separate video for that. But yeah, I will give a high level overview, and we'll iterate to my template code also with this video altogether. Yes. And then we have to recall that few things, like the node of a binary tree is a leaf if and only if it has no children. So I guess you guys is already aware of the leaf node. So leaf node is basically a node where it has no children associated with it. So if a particular node, let's suppose, has no children associated, so that that node we call as a leaf node. So here you can see it has no children. So this node we can say as a leaf node, but this node 5 is not, because for this we have two children, 6 and 2, right? And the depth of a root and the depth of the root of the tree is 0, and if the depth of the node is d, then depth of each of its children is d plus 1. Depth of each children is d plus 1. So now they are giving, I think it's also very straightforward also. So they are basically telling that the depth of the node 0, the root node is 0, the depth, because we are starting our traversal from root node generally on the binary tree, so we consider it's at the top level, so its depth is 0. And when we basically traverse further to our binary tree, then depth is also going to be increased. So if the depth of the node is d, so let's suppose, and another point, if we consider this 5 is at depth as d, so the depth of its children is d plus 1. So it's depth of its children. So who are children? 6 and 2 are children. So if I consider this node as a d, then its children 6 and 2 are of depth d plus 1. So can I copy it? Is there an option to copy? Not sure. So what we can do, and take a screenshot of this tree altogether. Maybe we can use to our OneNote explanations with some pen and paper work, right? And the lowest common ancestor of a set S of node is the node A with largest depth, such that every node in S is the subtree with root. Subtree with root as A. I think these portions some of you guys is already aware, but if you not have that understanding, then maybe it's going to be a little bit challenging to understand. But it is a very common things, like ancestor of a group of nodes. So I will quickly explain. So the lowest common ancestor of set of S nodes. So if I can ask you, what is the common ancestor of 6, 7 and 4? So, or maybe we can jump to our OneNote altogether, because that portion is actually the critical part. We can small it, and now we are at this point. We can insert we can insert a picture from file. Open, be fast. Where we stored it should be in our screenshot. In screenshot, this mostly, yes, we got our tree. Make our tree a little bit bigger. Yes. So that is our tree. Now if I am going to ask you, who are, like, for this node 6 and this node 7, who are the common ancestor? Common ancestor? So who is the ancestor of 6? 6 ancestor is 5. Who is the ancestor of 7? 7 ancestor is 2. Are they common? No, they are not common. So 5. So what is the ancestor then? 2's ancestor is 5. 2's ancestor is 5. So can I say then, who is the common ancestor for both? 5 is the common ancestor for 5 is a common ancestor for both whom for both 6 and 7. 6 and 7. You guys got it, right? How we find? So 6 ka we search for parents, so it's 5. 7 ka we have find go for parents, it's 2, but they are not common. Then we from 2 we went to 5, and on 5 we can we find the intersection points where both the nodes. So from 5 nodes, both the nodes diverge. One node for which we are searching the parents, for which we are searching the ancestor actually, is belonging to 5 lefts, and 7 is the another ones for which the node is belonging to its right part. So on 5 we can say 5 is an ancestor. 5 is an ancestor for sure. 5 is an ancestor for sure. But now can I say 3 is also an ancestor? Can I say 3 is also an ancestor? Yes, why not? Why not? Because 3 is coming as a 5 parents, and from 6 we are going to 5, and 5 to 3, and for 7 2 to 5 to 3. So we can say like 3 is also a ancestor, also an ancestor. Now both are ancestor. 5 and 3 both are ancestor of 6 and 7. 6 and 7. So both kai we have ancestor of 5 and 3. Now who is lowest common? So both are common ancestor. Both are common ancestor for both. Now there is a term of lowest. There is a term of lowest. So what actually this means? Lowest means from the targeted node. So for our case the targeted node are 6 and 7. Who are lowest common? 3 those we are say it can be an ancestor, but which is the first intersection points where from which both the nodes diverge. Can I say it's 5? Can I say it's 5? Yes. So here 5 is the lowest common ancestor. So 5 is in that case is our lowest common ancestor, right? Now can you guys can we take one more example? For 7 again we are targeting 7, and let's suppose 8. 7 and 8. Can you guys tell me? 2, no. 7 to hai, like 7 is belonging to its left. 8 is altogether not belonging to its right. No. 2 is not. We move up. 5, no. 5 is also not, because 7th is belonging to its one of the part, but 8 is not. So but for this three 7 is belonging to one of its left part, and 8 is belonging to another of its right part. So for this case our answer should be 3. So 3 is the common ancestor, lowest common ancestor of both 7 and 8. I guess you guys got the gist, which is actually the lowest common ancestor. So now let again back to the problems altogether. So yes, now what else? Now so that is the question. Now you have to find like what is the deepest child, what is the deepest leaves we have. So for the deepest leaves, what is the lowest common ancestor? Of all of its deepest leaves? To all of its deepest leaves, that node pointer we have to return. So that lowest common ancestor node pointer we have to return. That's it. The question is as simple as that. So for this example you can see who are the deepest node. But very clearly we can say that 7 and 4 are the deepest node. This 7 and this 4 are the deepest node, right? Because they are, if I consider this as a level 0, maybe we can go to our one node. So can we erase these things? Yes, we are able. Let me just quickly do these things. So here you can see if we are starting from root node, considering root node as a level 0. So who are the deepest node? So again let's go to these things. So if I consider this as a d equals to depth equals to 0, so this all together this level is at depth equals to 1. This all node is of depth equals to 2, 0, 1, 2, right? And this all branch is at depth equals to 3, right? What happens? Okay, we are good. So this all together I can say these are my depth configurations. This all things are my depth configurations, right? So this things is my depth configurations. So now can you guys tell me who are at the deepest node? Who are at the deepest? Can I say this 7 and 4 are the deepest. This 7 and 4 are the deepest because they have at depth 3. So for depth deepest node we have to tell if there are for our case, there are two deepest node. There are two deepest node. There can be n deepest node. There can be n deepest node. So for them, we have to say the common ancestor. We have to say the lowest common ancestor. Lowest, and we already discussed how we can find the lowest common ancestor. So we know actually what is actually mean by lowest common ancestor, where all these deepest nodes has just merge. All the deepest node just merge to that node. We can say this as a lowest common ancestor. So 7 and 4 are our deepest children, right? Deepest leaf node. So for this particular test case, we have two deepest leaves. So for them, we have to find who are the lowest common ancestor among them. Who is the lowest common ancestor of two of them? So if I can move from 7 to 2 and I have moved from 4 to 2. So can I say this is the junctions? This is our junctions. This is our junctions where this bifurcations has done. Where this bifurcation has done. And if we are pinpoint our point of junctions, can I say this is our lowest common ancestor? Yes, we can. So for this particular test case, you have to return two node pointer, node to's pointer you have to return. I think they have explained the same things, but I have like visualized and explained you the same thing. So here you can see we return the node with value 2 colored in the yellow. So that we just explained. So we have to return two nodes, node pointer. The node colored in the blue are the deepest leaves. We already know 7 and 4 in the deepest leaves. Note that the 6, 0 and 8 also leaf nodes. So 6, 0 and 8 are also leaf node, but the depth of them is 2. But the depth of 7 and 4 is 3. So that we already explained. So what is the depth of 6, 0 and 8? This leaf nodes. This is 2. We have already explained. And for 7 and 4, it's 3. So they are deepest. So we have to find lowest common ancestor for 7 and 4. And for 1, it should be 1, and for 0, 1, 3, you guys can draw the diagram, and for that case, the test cases will be coming as a node 2, right? Yeah, so now I think we guys are able to understand the problem statement. Now on the solution part. So can I say we can use the lowest common ancestor code as it is? But yeah, before go to the lowest common ancestor, so I am assuming you guys has high level idea of how actually the lowest common ancestor is in general, like very interview intuitive, I have to say, like interviewer like to ask, or like most of the interview, like if it is a lowest common ancestor, they will ask this question only. So that is basically something like this. So they will give you two nodes. So they will give two nodes pointer, node 1 and node 2. They will give two node pointer, node 1 and node 2. Now they will ask them and they will give a binary tree. So this can be anything, right? This can be anything, and it can be as big as possible. So they will ask, what is the lowest common ancestor of node 1 and node 2? What is the lowest common ancestor of, let's suppose node 1 belongs to here and node 2 belongs to here. Can I say this is our lowest common ancestor? From here both are diverge. Yes, so that should be our answer. We have to return the this node pointer. So that is the very standard question. Can I say we can use exactly the same template for this particular question? What actually changed here? So rather than two nodes, can we apply the same? Can we apply same things for n nodes? Yes, I think it's yes, but we still not know. So if I am going to tell, we can use, but before that you guys definitely ask me. So please then explain how for two nodes it is working. Then maybe by solid proof we can consider, we can make it generic for n nodes. But before that, please Shouvik, give some solid proof how for two nodes it is working. So for two nodes it's very simple. So for two nodes, what actually the things? So if can I say if our node, if the node is altogether a none, if our node is altogether none, then on that case we don't have to do anything. So we can return a none. So with traversing we are landed to a none node. So altogether we have moved to the out of the tree boundary. So then that case we are returning a none node. But if the current node is altogether equals to my node 1, or my current node is altogether my node 2. If they are exactly of this node, can I say like for them if they are exactly the targeted node, so can I say the lowest common ancestor for them is the node itself? Can I say? I guess yes. So if I can ask you, because we are doing BFS. So initially we will be here, then we will be here, then we will go to left and right, then we will again explode to this, then it's left, then again it don't has right, so we are going to here, and after that we are going to this left, and post that we are going to this right. So that is our traversal, that is our tree traversal algorithms, like this way, which I just saw. That way it will move. So let's suppose if I am going to ask you what is the lowest common ancestor of this and this. So if you are standing at this particular index, so can you say this, let make myself as a ancestor. Let make myself as an ancestor. Okay, fine. Yeah, because at the time of traversal, let's suppose we reached here, and this node is giving, but for our case answer should be this, which I am highlighting. So answer should be this, but this node is stating that, okay, for my case, as I am a part of a finding node for which you are finding the lowest common ancestor, so I will be going to return myself. Okay, fine. So that is the another case. Now otherwise we will call our helper function. We will call our helper functions to node of left, and we will call our helper functions. We'll call our helper functions to node of right, right. We will call our helper functions for left and right. We'll definitely do. So that is, and after that we will do. After that we will do our job. So that is called actually post order traversal. That is a very popular tree traversal algorithms, but if you aware, then very good, but if you not aware, then please read these things. It is very simple. So it is something like this. If you call the functions earlier, and with the function results, if you want to do some modifications after the functions call, then that is called a post order traversal. It is the general template of that, but if you at some points, if you are not able to understand, please make a comment. I will make a separate video of pre-order, post order, and in order traversal. That is very simple. But yeah, so that is the generic template of how actually the post order traversal we write. So that is a post order traversal for sure. Now let's suppose now this current node is not a targeted node which you are looking for, because for targeted node, from here we are altogether returning that itself as an ancestor. But so this for the node for which we are writing the if, so for this I am definitely sure it is not the targeted node. Now what can be happen? Now if it's left and right is altogether giving some value, so that means it's from its left pointer also some node is stating that I am an ancestor, because I know whom I am looking for an ancestor by. But from here, if they are as a part of the ancestor, they are giving their itself node pointer to the backtracking parent function, to the backtracking part of the parent function. So if for a particular node left from its left call, someone is stating I am itself my ancestor. Some right part is stating I am is my ancestor. I am it's my own ancestor. So can I say this particular node can return himself? Yes, because if you can look to our tree, so this node return as a or maybe I can write something like this, return as a node 1, and this node return as a node 2 to its parent function. So after this traversal, because for our case, how the traversal worked actually. So if I can again draw the tree, quickly draw the tree for you. So this node is this, then call is going to be back. So when call is going to be back, so here node 1 has calculated and it's stored in left variable. And then this function is making its right call move this, and this function's return, and this like this way return. So node 2 is going to be stored on right. So for this particular node, it's from its left, some node is stating I am ancestor. It's right, someone is stating I am my ancestor. So what is the decision this node can take? So this node then make us more intelligent move and can say, hey, I am the lowest common ancestor, because my left some portion is exist, my right some portion is exist. So then I am my lowest common ancestor. And right, so that is another case. So that is the very standard template, guys. If you not aware, then I will definitely suggest you to read it. So that is my own template. But at any point, if you guys not able to understand, please do a comment. I will make a separate video of my lowest common ancestor template. But I'm giving a high level gist, not a high level gist. I'm giving the complete gist on this video itself, because that is the base of this particular question. And then what left? So we have handles. If left say we are getting some value, right say we are getting some value, then this node is returning itself as a value. If that is as a targeted node, then also we are returning this node as a value. Now what else? Now if you can see now, if this node is, so this node is returning the answer, this node is returning the answer. So for this node left say to we are sure we are not able to find anything, so from left we are getting a value of none, that is null altogether. But from right we are getting node, we are getting our answer. So if a particular node, so now the case if a particular node, if we are getting a value from the particular node from its left, maybe, then not do any brainstorming on the current node, return as it is the left node we are getting. And if we are getting value from our right node, then also don't do any brainstorming, return right node altogether, right? This is very simple case. And let's suppose for this particular node which I am highlighting, for this left say it is none, right say it is none, so this node can return altogether as a none, as a none, right? So there are 4 cases: left set, right set, return itself, left set, right set, return itself, left set, return left, right set, return right. No, any left is not set, right is not set, return none. And if any of them is the targeted node, is the current node is the targeted node, then return itself. It is as simple as that, guys. It is as simple as that. So that is my own template. Now can you guys say this template is exactly work for our use case. So rather than two nodes, if I can again draw our tree, and let's suppose if for this particular tree, how many deepest leaves are possible? This all four. So what is the tweak we have to incorporate? So rather than checking this node current node equals to node 1, or current node is equals to or current node, this should be or my current node equals to node 1, or my current node is equals to node 2, then we are returning node, then I am returning my node, So rather than, now we have a set or list, a kind of collections of data structures. So rather than writing this, can I say if my current node in set of deepest leaves, then on that case we can return the current node. On that point we can return the current node. Yes, guys, yes, we can do. And that is the exact tweak. So we have to make our own template, and it will work as it is. So that is actually the brain, guys, for this particular question. We did a great whiteboarding, I have to say. But yeah, so before that, you guys have to know how to find the deepest leaves, and you can store this deepest list to the set, which set we are pointing here. So you can store this to this particular set, and you can check if your current node is belonging to this deepest set, then you can easily say that yes, it is a part of my deepest leaves. Yes, then on that case you can return the current node value. Right, guys, it is as simple as that. Now I am going to iterate you to the code itself. I am pretty sure, so you guys will definitely get the deepest nodes code the way I have written. So yeah, so let me just explain the code template to you. So initially I have declared some class level variables to it. One is storing the max depth, and another one is storing the max depth nodes. So that is the set. So on max depth, which are the nodes we have? Which are the nodes we have that is stored by this max depth nodes. Now we are calling our helper functions with root, passing root, and root node depth is 0. That is already mentioned in this particular question. So here you can see the number of nodes on the constant. It is from 1 to 1000, and the values of the nodes of the tree are unique. So why they told us uniques? Because otherwise, if there are more occurrence of 1, then we are not able to build this set altogether. Because for one with node value 1, we have multiple nodes. So if we are pushing node 1 as the deepest node, so maybe one node is the leaf node, and another node with value equals to 1 is altogether not a leaf node altogether, but maybe we are going to push it. So to make that to a simpler path, they have already mentioned that all the node value are unique. All the nodes of the tree has a unique value. So unique means unique value, right? Yes, now we are doing the standard traversals on this. If node is none, then though we don't have to do. And if which portions I am explaining the correct portions. If our node and right, node left and right are equal, and my left is none, so that means that's the conditions of leaf node. That is the conditions for leaf node. So if that is a leaf node, then we know we have to do certain operations. We have to do certain operations. So what is the operations we are doing? We are checking if our max depth, what is the depth we are stating. If our max depth is equals to depth, so then on that case we can insert the current node value to our max depth nodes, max depth nodes, because we are sure this particular node is also a part of our max depth nodes. But if our current depth is more than what is the max depth we have initialized to our class level variables, if it is more, then can I say, okay, now I have identified a depth which is more than the max depth I have still encountered. So I have encountered a depth which is more than my max depth, I have still encountered. So on that case, make the correct depth as a max depth, reset your max depth nodes, and insert the current node value to your max depth nodes, because our max depth nodes is altogether should be reset with the current node value, and all the other value is not actually our max depth, because we are able to find a depth which is more than our max depth, and we have reset. And I think it's very self-explanatory at the same go. And after that, if for the leaf node, if we are good with performing these operations, we can return the functions. And after that we are making the functions. So in this you can see, right? So we are doing our job first and then making the functions call, So that is a pre-order traversal, where you are basically do your job first and then you are making the functions call. Then that is the template of pre-order traversal. On the helper functions, this helper functions, we are doing the pre-order traversal, right? And we are making our left calls with depth plus 1 and right calls with depth plus 1. And like this way, when we done to this our first iterations, we have these things ready. We have these things ready. We have our max depth ready, and also on our max depths which all the set nodes, because we just saw, right? We actually need this set. To use our template as it is, to use our template ancestor template as it is, we need this set altogether. When we have this set altogether to our hand, we should be good. So by the first traversal, by the first helper functions traversal, we are able to build the first things. And now the second call. So here you can see, like I have written two helper functions. Now you guys are if you know method overloading, I think you guys should know method overloading. So one with what is method overloading? A same functions is going to be called with different arguments, with different number of arguments, different data types of the arguments. So on that case, the two methods are on name same, but they have different arguments, or they have different they have differentiated by their arguments, data types, arguments number, something like this. So this is actually a classic example of method overloading we have used. And second functions, we have used our standard ancestor template as it is. So if node is none, then return none. And if this particular node value in our self of max depth nodes, which is actually our set, which is actually the set we are looking for, if that is so, then why not return node? So on other case, on the generic template, we are checking if the node value is equals to our left, or if our node value is equals to the node 1 targeted or node 2 targeted. But here we have to check to the set or the collection of the max depth nodes. So if that is so, then we know on that case we have to return our root node. We just did the whiteboarding on our one node, and then we are making our functions call. So that is the classic example of post order traversal. We done the traversal first. After that we are doing the calculations. So that is called as a post order traversal, and we are calling our helper for node of left, we are calling our helper for a node of right, and we have something to our left and right. And if both our left and right has something, so this node is taking the decisions. Hey, I have something as my left, I have something to my right, so I am the ancestor, I am the lowest common ancestor. So he is basically stating, he is basically throwing by backtracking to himself node pointer to its parent, himself node pointers to its parent. And if that is not the case, then maybe left is set. Okay, if left is set, then return left. Maybe right is set. Okay, if right is set, then return right. Or maybe the case none of them set, none of them is set. So on that case, return. And finally, we are returning what is the ancestor value we are getting to from these helper functions. We are returning at the value. So that's it. It is as simple as that, guys. It is as simple as that. So now quickly discuss the time complexity for this particular solutions. So how many times we are visiting a particular node? I think one visitations we are doing by this. and another visitations to everyone we are doing this by this helper function. So I have to say it is a big of 2n for sure. And on space part, I am not considering auxiliary space complexity, because for every tree it is the general things we will auxiliary space we can avoid. We have to make this pre-order, post-order, in order that generally takes some DFS stack trace. So but that stack recursion stack space we can ignore, that is very generic. But apart from that, what we are using a max depth nodes set, so that can grow as big of n, as big of n, on which case it can grow, guys, as big as big of n. Which case, can you tell me, guys? It not as big of n, but it is for sure of big of n minus 1, big of n minus 1. Can you guys tell me? I think it's very simple. So if we have a tree something like this, this I think you already saw this. Okay, that is a binary tree altogether, so that is not possible. Yeah, I think binary tree, then what is the maximum depth can be? That can be like because from here it can't have, so it can, so there can be like at max I think 2 nodes only, like or on this particular test cases you can see, like if I can keep on writing these things. So this actually can grow, this actually can grow on first levels we have 2, on second we have 1, then 2, then 4, right? Then how many? 8. I think if we are hitting 1000, it is kind of a logarithmic. It is going to be a logarithmic. So it can grow. It can grow as, so max depth nodes as big can be of log n for sure. It can go as big of n, because you guys got it right. So on first we have 1, 2, 4, 8, then 16, like this way, and all of the summations of the all nodes present should be under 1000. So considering that for every nodes we have a into 2 factor between its just previous, so that means its height can grow as big as like log n depth, and on the on the very last, if you can sum them up to the 1000, it can grow of logarithmic of 1000, you can say. Yeah, so that is the time complexity and space complexity of the most optimal solutions, I have to say, because my submissions is you can see it is like 100% faster. It's almost run in 0 milliseconds. It's not actually taking time altogether. So, but yeah, like some microseconds, it's obviously took some time. But yeah, it is like 100% faster of all the submissions we have in the Leetcode. Yeah, so and that's it, guys. That's like we have two loops, two basically traversal. First one is for like basically getting the max depth nodes ready, and after that we used our own very generic templates altogether for finding the ancestor. So the time complexity is going to be a 2 plus kind of big of 2n. So that I am pretty sure it should be like the most optimal solutions for this. And space perspective also, we should have to store the max depth nodes to some data structure to calculate. Yeah, so that's it for this particular solutions, guys, for this particular question solutions. And if you guys are able to understand that, if you are following us till this point, please do subscribe to our channel, and please turn on the notifications so that when we are going to be live to our next video, and please share the videos to your connection so that also they can get the most of it. We have created separate playlist now, so we have DP playlist. We will start with this, the tree playlist also. So this video is definitely going to be our tree playlist. We have 4 videos on like very difficult algos like disjoint set, DFS, BFS, and then topological sort, and like most complex graph traversal algorithms has covered like 4 videos. Like Leetcode has throw the questions of graph, and we have able to solve all of them, and the graph playlist has few set of good videos. Please do check them out. Check them out. So that is the very standard questions based on graph. So we have categorized our playlist based on the problems we are solving. So please go to the video and please do your own submissions. Please write your own on your own word, because if you are only watching the videos, that is not going to help you guys on the longer run. So please try to solve the question on your own, and please do the submissions on your own code, and like this way you guys actually make your thinking ability, make your problem solving ability to make it on a different level. So that's it, guys. And weekends has already arrived. I am planning something like great contents I can put on the weekends perspective, because you guys know on weekends I am trying to make some new topics, or make some like different kind of video, which is not actually the very standard problem solving kind of things. But yeah, problem solving videos are going to be coming, but I am planning to make some like different things. If you guys following us, one, we have make a resume review, another one is we went for a trip, we captured those. Yeah, these things, let me think for this weekend if I can plan something good for you guys. So that's it, guys. That's it for today. Let me tomorrow with another beautiful question, and enjoy your weekend. So that's it. Bye guys. Bye bye.